Welcome to Lecture 9 of Introduction to Computer Architecture. I'm Simon Moore, and today I'm going to tell you all about hardware support for operating systems. In this lecture we're going to look at a number of different components that are needed to support operating systems. And for example, a bit later on we will look at different privilege levels and how to transition between them. But to begin with, we're going to look at virtual memory. So the idea with virtual memory is it gives the illusion it gives each application the illusion that it has its own address space. And the processor provides some low-level mechanisms that the operating system exploits to translate virtual to physical addresses. So the idea is that applications work with virtual addresses and the processor does that translation efficiently. Memory is broken down into pages, quite often 4 kilobytes, but sometimes more, and also super pages. Actually, page size does vary quite a bit. For instance, on iOS, for Apple phones, the page size is actually 16 kilobytes, whereas actually for PCs, the default on Intel processors is 4 kilobytes. Each translation fault is called a page fault. So virtual memory aids in memory allocation because it means that the operating system can allocate additional pages of memory to an application dynamically, and there doesn't need to be a sort of linear mapping between linear virtual addresses and physical addresses. We'll see a bit more about that in a minute. It also provides memory protection. In fact, some of my colleagues would even say that it conflates memory protection, but we do currently use virtual memory for protection. It adds permission bits per page to determine what is shared and what is not. It also allows rarely used pages to be migrated to disk in a process called paging. This gives the illusion of a bigger memory, and it can be useful to tolerate long-running applications that have slight memory leaks, because the operating system can start identifying which pages basically aren't being touched, and those get paged out to disk, and effectively it sort of means you're not using up physical memory for dead memory spaces. However, paging is very slow. It's very slow if you're going to magnetic disk, although it was used a lot, particularly in sort of legacy systems, and it risks wearing out flash disk if you're using SSDs or NVMe based storage. So actually, paging is a bit tricky these days. We've sort of gone through an interesting phase with paging. For older systems, when we just didn't have an awful lot of memory, paging was pretty essential. Although even then, you could easily hit a wall if you didn't really have enough DRAM to store all the active pages and you ended up paging a lot of memory out to disk. You could basically fall off a performance wall cliff, where you're spending all your time paging and not getting any useful work done. And in fact, where we do use virtual memory on some modern devices like like smartphones, they do use virtual memory for protection and memory allocation, but they don't page. Typically, they don't page, and instead, what they tend to do is just start killing background applications in order to free up memory. So let's look at the basic concept. So here let's assume we've got fixed size pages of 4 kilobytes for normal pages or 4 megabytes super pages, and we've got a figure here that looks at virtual to physical address translation. So we've got some mapping between the virtual addresses of one application and which bits of physical memory it uses, and it won't obviously be using all the physical memory. In fact, often an application is only using a small proportion of physical memory, and so there'll be many arrows. There won't be that big a density of arrows from the virtual space to the physical space. We've also got some pointers to areas on the disk. And here we've got a very simple example. This happens to be for a 64-bit machine where we've got a virtual address, and we use some number of bits in the virtual address, and they get translated to a physical address. And we're going to see how the translation works in just a moment. Actually, there's a couple of things to note for 64-bit machines that are different from 32-bit machines. So on 32-bit machines, you tend to use the entire address space. You'll have the complete 32-bit virtual address space, and obviously 2 to the power 32 is 4 gigabytes. And that's one reason why, of course, some high-end mobile phones now use 64-bit processors, because you want to access more than 4 gigabytes of physical memory. And depending on the 64-bit machine, it may well be that you actually have a smaller physical address space, and these tend to be sized for the sort of system that this processor might be used in. So if it's just, sort of desktop PC system, you might assume that, for example, you can only have 64 gigabytes of memory, whereas if it was a server grade processor, you might allow, half a terabyte or even a terabyte of DRAM. And this sort of simplifies the translation mechanism, as we'll see in a minute. Anyway, that's a bit of a detail. Page tables store the virtual to physical translation information. So these are set up by the operating system for the processor to use. Okay, so there's sort of like a partnership between the OS and the processor. So page tables are basically an array of page table entries, or PTEs, and they're indexed by the virtual page number. We have a page table register in the processor, and that points to the page table in physical memory. And typically this gets changed every context switch, because you tend to have a separate page table for every application. So if a page is present in memory, the PTE, the page table entry, stores the physical page number plus other status bits. So, referenced, whether it's been dirty, there'll be permission bits, and so on. We'll see more of that in a minute. If a page is not present, the PTE can refer to a location in swap space on disk, and then typically a software page fault handler is invoked. So a page fault is taken when the PTE entry indicates that the page is on disk. Or case, of course, the page may not have been allocated at all, in which case it's a fatal exception. The application wasn't allocated any memory there. In any case, software, usually some privileged software like the operating system, has to get involved at this point and decide, well, what should be done. If there's a page fault and there's just that memory should never have been allocated to the application, then it may well be that the application is just shut. So it'll be core dumped and closed down. If the page is on disk, then we'll want to go and find it. In order to figure out what's going on, the OS will know what the virtual address was, and we'll see how that works in a minute. Typically the virtual address is stored in some register. That virtual address is used to find the PTE, and then the OS can determine if the page is on disk, so it can then locate the page on disk if needed to. It can choose the page to replace, and also there's usually a page dirty bit. So if the page has been written to, it's marked as dirty, just as in caching, and if it's dirty, then we have to write the current page that we're going to replace to disk. Obviously, if we've got some free memory, then we just use that. But typically at the point when we start paging, we haven't got any free physical memory left. We then read the page into memory and update the page table entry, and then we make the process runnable again, in other words the application. So we actually want to restart the application from where we left off. And remember, I was talking a previous lecture about precise exceptions, and this is a good example of a precise exception in that we want to be able to restore the application and get it to run, right at the point where it faltered a load or store instruction, and we want it to be able to rerun that instruction and just continue as if nothing had happened. So, from a functional point of view, for that application, paging is completely transparent. It will have a major performance impact, however. Let's think about the page fault penalty. So on a page fault, the page must be fetched from disk, and that's obviously handled by the operating system, and this can take millions of clock cycles to go and fetch stuff from disk, get it into memory, swap things back and forth. Obviously we want to try and minimize the page fault rate. First thing that really helps is through the virtual physical mappings that we can actually have a fully associative placement. So any page on disk can be mapped to any page in memory. Similarly, any virtual address or any virtual address that refers to a particular page, that can be mapped to any page in memory. So that's very helpful. That tends to allow us to really optimize things, and so there are then all sorts of smart replacement algorithms to make this really efficient. So let's just summarize this mapping of pages to disk problem. Effectively, the DRAM becomes the cache of the disk, if you like. Disk accesses are slow, so careful management is critical. So as I've already mentioned, we need to have a dirty bit. So if we've never written to a page, we don't need to write it back to the disk, and that'll save quite a lot of time. We'll still have to read a page from the disk. Page table allows basically a fully associative mapping. So it's not, we don't need to search the entire page table. However, we do just basically take the virtual page number as the address and use it as an index into the page table. So that's very straightforward. But each entry in the page table can point to any region of physical memory and any block in our swap space on disk. So that's why I say it's an associative mapping. And we tend to use a least recently used policy when it comes to replacing pages. Let's look at how we actually make all this translation process efficient. So we're going to look at the translation look-aside buffer, which is some hardware provided by every processor, which caches PTE entries. So why do we need this? Well, address translation would appear to require extra memory accessors. So basically, if we didn't cache PTEs, then every time we want to access memory, we would first have to look up in the page table what the virtual to physical mapping is, and then do that actual memory access. However, page tables have really good locality. So, they also have, it's basically we're exploiting temporal locality. Okay, we're not looking at spatial locality here, however, we're just looking at temporal locality. In other words, if we've accessed a page, there's a really good chance we're going to access a page soon. And if you think about this from the point of view of a piece of application code, this makes a lot of sense, because you're often running, a particular piece of code, so the actual, the page that's holding the code, we're just going to be working through that code for ages. And similarly, on the data side, we're going to have things like the stack, that's going to just sort of sit in a few pages, and we'll have some other memory, and depending on how that gets used, we may not touch all that many pages, certainly not over a short period of time. So we can basically have a cache of PTEs within the processor. That's called a translation look-aside buffer, and typically they're of the order of 16 to 512 PTE entries, although you can now have sort of multiple levels of TLB and all sorts of things in much the same way that you can have multiple layers of caching. Actually, for a very small TLB, ARM processors quite often have what's called a micro TLB, which is a really tiny TLB, and that's accessed very quickly with it, much less than one clock cycle. And they need that because on ARM they always do the virtual to physical translation before they do the L1 cache access, so it's got to be very quick. On RISC-V we often actually do the translation in parallel with the L1 cache access. In other words, we do virtual indexing on the cache, and I'll talk more about that in a minute. So TLB is typically pretty quick to access. If we get a miss, then it's going to take 10 to 100 cycles depending on how far the miss needs to propagate to actually fill it. And ultimately, of course, we may get a page fault, in which case the OS gets involved, and then it can take literally millions of cycles. So the L1 lookup is quite often performed before the L1 cache access, as I've just mentioned, and the TLB misses could be handled by hardware or software. In older processors like MIPS, it was often handled in software, but actually more modern processors, so Intel, ARM, and also RISC-V have hardware page table walkers. So these basically go and fetch the values into the TLB, and we'll see more about the structure of these page tables and what the page table walker does in just a minute. So let's sort of summarize the idea of that fast translation using TLBs. So here we've got a TLB at the top of this figure, and that's got a virtual to physical translations in it, and it's a cache, just as in the data cache. So it also sort of has tag information as well. So we basically take a sort of hash, or we might even use a fully associative lookup on the TLB. In fact, if the TLB is quite small, they're quite often fully associative. Otherwise, they might be set associative or direct mapped, just as a data cache. And then the translation entries are used to point to physical memory quite directly. Otherwise, we actually have to look at the page table on disk. And as I said, the page table in memory rather, either gets looked up using hardware or software. Typically these days it's hardware that does that, and we only invoke software if we actually need to refer to some memory that's been swapped out to disk. So on a TLB miss, if the page is in memory, then we just load the PTE, the page table entry, from memory and restart. And as I said, it's usually handled in hardware these days, though it can get complicated for more complex page table structures, but it's usually worth it for increased performance. The other problem, of course, with baking in the PTE lookup in hardware is that it typically restricts us to one form of page table structure. So certainly some older processors preferred to do the page table lookup in software, and here a special exception is usually raised, and there's usually a very optimized exception handler in order to basically fill the TLB entry very quickly using software. And if the page is not in memory, then we get a page fault, and then we do have to invoke the OS, and the OS has to go and fetch the page, update the page table, and then actually restart the application. So for a hardware page table walker, obviously the TLB miss causes the hardware software page table walker to search for the PTE, and so it really is the case that the TLB is just a cache of the page table. The PTE found gets put into the TLB, and if the PTE is not found, it results in an exception, and we fall through to the OS. Quite critically, in order to preserve our nice simple sequential execution model, and for the application to be unaware that it's really running in a virtual address space, and for all this stuff to be completely transparent to it, we must ensure that the TLB miss is handled before any state is updated, like the destination register. Also, typically memory operations are replayed, so this will be either instruction fetch if the fault was during instruction fetch, or if it's a load or store operation, then the processor has to actually arrange that those load or store operations actually get replayed. So in other words, we typically go and fetch the load or store operation again from memory and actually replay that instruction, so to re-execute it down the pipeline for that to complete. Now let's have a look at page table structures. So here we're going to focus on the 32-bit RISC-V paging scheme. 64-bit is similar, it's just a bit more complicated, and it gets hard to fit it on the slide, so we're just going to stick with 32-bit. So we've got a 32-bit virtual address. The bottom 12 bits, this is assuming we've got 4 kilobyte pages, is just the offset, it's the byte offset within the page, and then the upper 20 bits, here we've split into 2 lots of virtual page number, and we'll see why in a minute. And we have to use that virtual page number to look up the page table entry in memory. Okay, we'll see in a minute how to do that. The actual page table entry, when we look it up, has 2 components of physical page number. We just basically concatenate those bits together. It also has RS and W bits that are reserved for the supervisor. We've got a dirty bit, an access bit, a global bit, a user mode, execute, write, read, and valid flags. Okay, that are all stored in the bottom 12 bits of the page table entry. And the basic idea is that once we've got the final PTE, we just assemble the physical address by using the physical page numbers, the PPNs, and the page offset. And then we're good to go. We've done our virtual to physical translation. So the real trick here is knowing how to do that lookup from the virtual page number to the page table entry. Let's just look at the execute, write and read bits in a little bit more detail. So here they are tabulated. Most of them are fairly obvious. You could have 0 for X, 0 for W, and R for read means it's a read-only page. You'll notice that some of them are marked for reserved for future use. So for example, we can't actually have a write-only page. It'd be a slightly odd thing to do. We also can't have a page which is execute, write, but no read. So that's not allowed. The other thing to note is the very first entry indicates, of course, if the page has no read or write or execute bit set, then basically you can't access the page isn't valid. However, we're actually going to use this as part of the multi-level page table structure, and it means that the page table entry is actually a pointer to the next level of the page table. Actually, moreover, the check whether it's a large page is whether a read bit or an execute bit is set. And you'll notice that in all of the valid entries. We can either read or execute or both, but never none of them. So let's explore multi-level page tables. And firstly, let's think, well, why do we need a multi-level page table? Well, if we had a single level table, then we would need to translate all of those virtual page table bits. Remember, there's 20 of those on a 32-bit machine. Each page table entry is 4 bytes in size. Therefore, we'd need 4 megabytes, which is a fair bit of memory. And remember, this is the amount of memory you need per application. And also, quite critically, much of the space is unused. Most applications don't use all of the physical memory. So really what we need is a better data structure. And that better data structure is a tree-based page table representation. Each section of the page table fits into a 4 kilobyte page, so that's 2 to the 12 bytes, where the page table entry size is 4 bytes. The Supervisor Address Protection and Translation Register, the SATP, holds the base of the tree in the physical page number field. So what we do to do the first lookup is we compute an address based on the physical page number in the SATP. We multiply that by the page size, and that basically gives us the base address for the table. And then we simply add on the top bits of the virtual page number, so VPN1 multiplied by the PTE size, which is 4 bytes, and that gives us a byte address. Now, if we when we look up that page table entry, if the X flag or the R flag are 1, then it's marked as a super page. Okay, and for super pages, the PPN 0 value will be 0. And in which case we're basically done. We've done all the lookups we need. Otherwise, the lookup address for the next entry in the page table comes from the 2 parts of the physical page number multiplied by the page size, and then we add on the VPN 0 value multiplied by the PTE size. Of course, if we've got a 64-bit machine with 64-bit addresses, then we've got more levels of translation, but we're not going to talk about that on this course. So let's look at how we actually handle super pages, and this is specifically for 32-bit RISC-V. So here's our virtual address as before. So we've got our virtual page number that's split into 2 components, and we've got a page offset, which is a byte offset within the page. So we take the most significant bits of the virtual page number to give us our first lookup address, as I just described. We do a lookup in memory, that gives us our first page table entry. And here, by definition, if it's a super page, it must be read or execute set. In which case we know that the physical page number, the lower bits of the physical page number have got to be 0. And in which case the physical address is simply formed of the upper bits of the physical page number that we've looked up, and then we use all of the lower bits of our virtual address to form the final physical address. Okay. Now let's look at how we handle a 4 kilobyte page. So we start again, as always, with our virtual address. We do the first level lookup exactly as before. However, here we discover that read and execute bits are set to 0. So we've got a further level of indirection to do. Okay. So the next lookup address is as follows. we've got the PTE lookup address is formed of the concatenation of the bits of the page number multiplied by the page size plus the VPN number multiplied by the PTE size, okay, VPN 0, and that gives us the next lookup in our table. So we do a further lookup to get us our next table, and that finally gives us a new physical page numbers, and at this point either read or write, read or execute must be set. And at that point we just take the physical page numbers out of the PTE, we insert the page offset from the virtual address, and we've finally got our physical address. Let's look at the memory protection offered by virtual memory. So different applications, processes or tasks are allocated their own virtual address space, and we have a pointer in hardware to the page table which is typically changed during a context switch, and on RISC-V that's called the SATP. The SATP includes a 9-bit ACID address space identifier, so that we can sort of detect, so we can have lots of separate address spaces, particularly in the TLB. In other words, if we're context switching a lot, it means that we don't necessarily have to flush the TLB. Okay, so the TLB has entries that includes the ACID, and so we don't get confused by translations in different address spaces. Different applications can share parts of their virtual address space, but obviously need to protect against errant access, and so this needs to be configured via the OS. Typically you just end up with a few shared pages and a lot of other pages that are private to the applications. And finally, to sort of go with all of this memory protection, we're going to need some sort of privileged mode, supervisor mode, or sometimes called a kernel mode. We're also going to need some privileged instructions, potentially to set up things like the SATP, because we don't want an application just changing their own address space. And we need page tables and other state information only accessible by this privileged code, by the supervisor code. And we're also going to need some way of transitioning between protection domains. So we're going to need something like a system call exception, eCall as it's named in RISC-V, but other machines call it, a software exception or syscall or something like that. So we have a number of operating modes on RISC-V. Level 0 is just the user mode or application code, so that's the least privilege. Level 1 is the supervisor mode. That's if we've got virtual memory and so on. We tend to, the operating system normally runs in supervisor mode. There is also level 2, which is currently reserved, and level 3 that is machine mode, and that gives very much unrestricted access and is sort of a lower level mode. If you don't have virtual memory, then RISC-V processors tend to just have user mode and machine mode only. The modes control access to privilege instructions. They control access to how you access memory. So obviously in user mode, if you've got virtual addressing, then virtual addresses are used everywhere and you don't get unfettered access to the machines. It's very much restricted. You get limited access to privilege instructions. So privilege instructions are things like return from trap or interrupt, and some memory management instructions. And in user mode you also get limited access to certain control status registers, CSRs. There are some implementation choices for different sorts of RISC-V cores. Okay, so for a simple embedded system, everything might just run in machine mode. If you've got a secured, very simple embedded system, then you'll have machine mode and user mode only. And if you've got a full-featured core that will run a Unix-like operating system, then you have machine mode, supervisor mode, and user mode. So if we actually view these modes from a software perspective, then we get a number of layers and a number of different interface abstractions that software will build using these low-level hardware mechanisms. So we've got applications that run in user mode. They usually have an application binary interface, an ABI, to the operating system, so they can make operating system calls. And of course, operating system calls need to actually cause a protection domain change, because you're going to need to move from user mode into S mode, into the supervisor mode for the OS layer. Okay, so a lot of the trusted code runs in the operating system, but you also may have a lower level code that runs in machine mode that, for example, might be provided by a basic BIOS or basic I/O system that's used to boot the system. And so you've got a supervisor execution environment which runs in machine mode, and in which case there is a supervisor binary interface that sits between the operating system and that lower level mode. So we have an environment call mechanism, which on some machines is referred to as a software interrupt or software exception. But on RISC-V it's referred to as an environment call. So we have this eCall instruction, which is used in user mode to call into a more privileged mode. So in user mode it'll actually be used by the ABI layer to transition from U mode to S mode. So the program counter where the eCall is in memory is saved to the EPC register. So EPC is the exception program counter register, and it's a hidden register. So it's not visible to user mode. It's only visible in supervisor mode. Okay, and note that the EPC is actually written the current value of the program counter. So in fact, when we do a return, we'll actually have to make some adjustments to that. Otherwise, we'd keep on calling the eCall over and over again. So EPC is the exception PC register that, as I said, that's hidden. When eCall gets called, of course, we don't want user mode to say which bit of the operating system gets called directly, because that would be a security problem. So instead, we have a machine trap vector that specifies exactly where we're going to jump to. And actually, there's two uses for MTVec. If the least significant bit is 0, then the program counter is simply set to the MTVec, and basically the operating system starts at that point, and it has to figure out why, whether it was an eCall or an interrupt or an exception or whatever, and do the appropriate thing. An alternative is to have basically a vector of program counter values. So it's sort of a jump table. And here we do a lookup in memory using the MTVec as the base address in physical memory. And to that we add the cores, which we multiply by 4 bytes, and that gives us a program counter value. Okay, so if the cause is 0, then it's actually the user mode software interrupt, and we'll look at the other causes in a minute. Finally, once we've completed our operating system call, we need an instruction to return us from a privileged mode into a less privileged mode, and that is the SRET instruction. So SRET is used to return from S mode to user mode, and it's used by the OS to do that protection mode transition, and basically it just takes the current EPC value and puts that in the program counter. So it's a bit like it's just like a subroutine return, but with the protection domain change. So let's look at the different interrupt and exception causes. So the first four in the table are all to do with software interrupts, so transitions between one protection mode and another. And as we've just been talking about the user software interrupt, which is code 0. We can also have a transition between supervisor mode and machine mode. So we can have a supervisor software interrupt. In other words, if the supervisor mode tries to do a software interrupt, that's cause 1. Code 2 is reserved. Code 3 is if the machine mode tries to do a software interrupt. Then we've got a number of causes that are to do with timers. So we can have timers at different modes. And then finally we've got external interrupts, and these are all to do with handling external events. So this might be some I/O device has completed, or we might have, received a network packet or something like that. So actually, let's look at those sort of the interrupts and exceptions in a bit more detail next. So interrupts and exceptions. Well, interrupts, exceptions, and software exceptions all use some very similar hardware. They all jump to some privileged code and change the privilege mode. Interrupts also cause a trap, but are based on external factors rather than actual instruction execution. So we've got examples here of, timer interrupts that are used for scheduling by the OS. We'll have DMA interrupts. So this is where you've got a direct memory access device that will be doing a block transfer, either from memory to an I/O device or from an I/O device into main memory, and we'll get an interrupt that indicates when the transfer is complete. We'll also have interrupts from devices, so things like network cards and so on. In contrast, exceptions are caused by the instruction stream itself, so we can have things like illegal instruction or division by 0. We could get page faults and so on. And finally, we've got software exceptions like equal. So let's wrap up this lecture and with a little summary. So hardware support for operating systems includes exception modes, so user, supervisor, machine. We've got exceptions and interrupts and software exceptions. We've got privileged instructions that are not available in the other modes. So this in particular will constrain what the user mode can do. We've got privileged registers like the EPC, the exception PC register, and we have virtual memory, which is great for memory allocation, and it's also used for memory protection. It should also be noted that different processors have different implementations of this sort of support. So for example, some processors, in fact most modern processors, have a hardware page table walker, but actually some processors rely on software to do page table walking and to actually update the TLB using software, using special instructions. However, despite the lower level implementation, they actually all provide the same basic abstraction. And this means that you can run user mode code using the whole notion of virtual memory without needing to know about the specifics for your application. Of course, the operating system is going to need to know a little bit about the specifics. So, there will be some OS changes between different families of processors if they handle things in slightly different ways. Nevertheless, as I said, it provides the same sort of basic abstractions. Right, with that, we're finished.